Welcome to another session with Ms. Taylor. We're going to talk about electron configurations and orbital diagrams. Now, what those things do are a way of representing the arrangement of an atom's electrons. Why do we care about that? Well, the arrangement of an atom's electrons determine its chemical properties, and that is what determines whether or not something reacts, the compounds it can form, and a lot of other properties. So before we jump into actually doing that, there's 3 rules that you need to know, and I'll point them out as we use them later. But the first is the off-ball principle, and that's going to determine our order of orbital filling, and I'll explain what an orbital is in a minute. But just know that it says that we have to go from the lowest state to the highest state. You can't just jump up to the second floor, you got to start from the bottom. The second is the Pauli exclusion principle, which says in an orbital there can only be 2 electrons and they have to have opposite spins. And we'll see this demonstrated when we write out an orbital diagram. The third one is Hund's rule, and it says you have to have 1 electron in every available orbital in a sublevel before you can double up or put 2 electrons in the orbital. So, little terminology so you can understand what those things mean. First thing is, what is a principal quantum number? That's your main energy level, and it's a number 1, 2, 3. The highest is 7. The sublevel is a way of describing the shape of an electron cloud. Okay, and you know that the electrons are found in an electron cloud, but we're getting into some detail of it. So shapes, and they have the letters S, P, D, and F, and the number of sublevels are equal to the principal quantum number. So level 1 only has 1, level 2 has 2, level 3 has 3, level 4 has 4, and so on. What is an orbital? Orbital is the specified area or space in an electron cloud where you can find a maximum of 2 electrons. Scoot this over just a little bit. Sorry. All right, so what are these sublevels, these shapes? All right, S, P, D, and F. The S looks like a sphere. Okay, it's round. And as you go up higher energy levels, they get larger. All right, and this is 1 orbital. So 2 electrons in an S sublevel. P looks sort of like a peanut. And there are 3 different p orbitals, so a p sublevel can hold a maximum of 6 electrons. When you get to D, they're a little interesting. I kind of described them as doubled peanuts to give you an alliteration in a mnemonic to remember this. So at least those 4 do, and then that one has a donut. But there are 5 different d orbitals, so a d sublevel can hold 10 electrons. We're going to need that knowledge in a minute. And then F, they're a little strange. You kind of think of them as flowers, though a couple of those don't exactly look like that. But there are 7 of them, and so an F sublevel can hold a maximum of 14 electrons. So, how do we actually write an electron configuration? Well, the first thing you need to know is how many electrons you need. Get that from the periodic table. Your atomic number tells you the number of protons, and as long as your atom is neutral, not an ion, it's equal to the number of protons. The second thing is having that order of orbital filling ready to go, and I've got it typed out right there. Now, how in the world are you supposed to remember this? I have a way of doing that. If you do not know the pattern from looking at the periodic table like I do, there is a triangle that you can draw, and I'm going to move our screen over here and draw this out for you. So what you would first need to do is draw the numbers 1 through 7 in a column. 1, 2, 3, 4, 5, 6, 7. Okay, and like I said earlier, the number of the main energy level determines the number of sublevels. So this is the main energy level we're looking at. So energy level 1 only has 1 sublevel. Energy level 2 has 2. Energy level 3 has 3. 4 has 4. 5 has 5, but there isn't an atom large enough to actually utilize that 5th one there. That would go there. And then there's the 6th and 7th. Notice that it creates sort of a triangle shape. Alright, and you should have 1 through 7 on the spine, and then as you go across the vertex, you have 1, 2, 3, 4, 5, 6, 7. Now that you have that, fill in the SPDF. So the first column is the S. The second column is P. The third column is D. And the fourth column is F. Now notice there is no 1P, there is no 2D. Those things don't exist because you can only have as many sublevels as the main energy level itself. Now here comes the slightly tricky part. You're going to draw diagonals from the upper right to the lower left, top to bottom. Okay, so... And what these diagonals are going to do is actually provide you that order that I had typed for you to the left. So if you follow from the top of the diagonal down, it gives you that same order. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. That is the exact same order as what is written over here. So, you need to memorize that so that you have that order, write it out, so then you can go on to do the rest of the electron configuration. So like I was saying, that first number is your main energy level. Okay, 1, 2, 3, 4. The letter is the sublevel, which is a certain shape that you saw earlier. And so there's a certain number of orbitals in each sublevel, and then each one can hold 2 electrons. So the number of orbitals you have times 2 gives you the total number of electrons. And then we will use an exponent on the letter to say how many electrons are in that particular sublevel. And you can double check your work by adding up the exponents, because the sum should be equal to the number of electrons that you are supposed to have, or your atom is supposed to have. So let's do an example. Let's take manganese. All right, manganese is element number 25 on the periodic table. So that means it's going to have 25 electrons. So when we start our order of orbital filling, we have to start from the lowest energy level, as the Aufbau principle says. That would be 1s. So 1s. S can hold 2 electrons because there's 1 orbital. 1s2. Your next is the 2s. 2s, 2. Keep filling. The next one is 2p. And there are 3 p orbitals in a p sublevel. Each can hold 2, so we will put 6. After 2p comes 3s, and that can hold 2 electrons. After 3s is 3p, which again, 3 orbitals times 2 electrons is 6. After 3p comes 4s, 2 electrons, and then the next one is 3d. Now here's where it's not going to be full, because up to this point we've got 2, 4, 10, 12, 18, 20 electrons. We only need to represent 5 more, so we're going to put a 5. So like I said, you can double check yourself by adding together your exponents, and that should equal 25. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 5 is 25. And that is in the correct order that we determined earlier. So there's your electron configuration. Not too bad. Okay. Now, the orbital diagram, it's an even more visual representation of this. And to draw an orbital diagram, you have to have the electron configuration, which we just did. Then you're going to draw a box or blank for each orbital and make sure you label them, and they should be grouped into a sublevel. So I've already got my boxes drawn for the sake of time. So this is your 1s, your 2s, these are 2p, this is 3s, this is 3p, this is 4s, and this is 3d. Notice that your boxes represent the number of orbitals in each sublevel, and you've got your sublevels grouped. Okay? The next thing you're going to do is put in arrows to represent the electrons, and you have to follow Pauli exclusion principle and Hund's rule. Pauli exclusion principle, as we said earlier, says that if you've got 2 electrons in an orbital, and that's the max you can have, they have to have opposite spins. We'll get to Hund's rule in a second. So these are full, so I'm just going to go ahead and draw in these arrows. Now when we get to 3D, this is where Hund's rule will apply. And Hund's rule says that we have to put 1 electron in each orbital in that sublevel before we double them up. So you're not going to put 2, 2, and 1. What you're going to do is put 1 in every box because we had 5. And that's following Hund's rule. So there's your orbital diagram. It is that simple. Now, you may be wondering, what do I do when I start getting to something that has like 100 electrons? Well, there is actually an abbreviated way to do this. It's called noble gas notation. And what it does is abbreviates it by using your last noble gas from the periodic table that was before your element. Okay, and then you just pick up from there. So in the case of manganese, element number 25, our last noble gas was argon. So what we would do is write argon, or AR, in the bracket. And remember, that represents 18 electrons. And then how do you know where to pick up? Fairly easy. You look at the row that the element is on, and manganese is on row 4, or period 4. And then you pick up from the S sublevel. So we would pick up from the 4S. So 4S. 2, because S can hold 2, that gives us 20 electrons. The next one is 3D, and we need 5 more electrons, so it's 3D5. So that is the abbreviated noble gas notation for manganese. You can also do this with the orbital diagram. Same thing, you would put your last noble gas in brackets and then only draw boxes for the remainder part. Okay. Now, a lot of this is very abstract, and so before I wrap this up, I want to show you a website that gives a very good visualization of what's really going on. And I'm going to move my box over here so you can see it. And this website, there is the address, but I put a link to it on my Edmodo page. Oop. Sorry. Alright, you're going to build a sodium atom. And remember, you're building it from the bottom. So, 1s, and 1s holds 2 electrons. Notice your orbital diagram being filled over there. Next comes 2s, and it's 2 electrons. After that comes a 2p. There's one of your peanuts. Okay, and you're about to want to drag another electron there. You can't do that. All existing p orbitals must be in place and have 1 electron before filling an orbital with the second electron. Ah, there's Hund's rule. So we drag another p over and put an electron in it. third p orbital and put an electron in it. And now that those are in place, we can put another electron in each of those. Alright, so after we filled 2p comes 3s, and we put 2 electrons in it. Okay, and we have gotten up to 2, 4, 6, 8, 10, 12. Ooh, we actually do not need one of those electrons there, but I don't know how to drag one out. So there actually should not be one electron right there. It should end in 3s1. But the visual is what I really wanted you to see. So I hope this helps. Good luck and good evening.